Atomic layer deposition, or ALD, is a process which can grow high-quality thin films using a binary sequence of half reactions, each depositing an alternate material at low pressure. ALD has the unique property of having self-limiting reactions, which allows for precise growth control over complex structures. Precursor molecules are delivered by an inert carrier gas and will react with all available surface sites, after which the reaction terminates and excess material is purged from the system. This occurs for each precursor type, resulting in the growth of a single atomic layer. This binary process repeats itself until the desired film thickness is achieved. The properties of the ALD film can be optimized based on the different deposition conditions, including the material source and deposition temperature, which can be as low as 50 degrees Celsius.
First, you need to prepare a template by anodizing aluminum. In this process, aluminum is oxidized and a porous oxide layer is generated. The diameter, length and distribution of the pores can be accurately tuned by using proper anodizing parameters. In the next step, silver is electrochemically deposited into the pores. As the oxide layer in the bottom of the pores is very thin, allowing electrical connection, the silver starts depositing from the bottom and eventually fills the whole pore. The surrounding aluminum oxide can be easily removed by simple etching in sodium hydroxide, allowing the nanorods to escape into the solution. The length of the current nanowires is several micrometers and diameter around 20 nanometers. They may be clustered at start, but can easily be separated by additional treatments.
Pulsed laser deposition is a physical vapor deposition technique that allows synthesizing thin films of a variety of materials. In pulsed laser deposition, electromagnetic radiation from a high-intensity pulsed laser is used as an energy source to evaporate a solid or liquid starting material, which is called a target. This laser is aimed at the target material, where the beam interacts with the surface and creates a luminous plasma plume. The plume itself consists of atoms, molecules, ions and electrons. However, in some cases, larger particulates and molten globules of material can be ejected from the target during evaporation. Some of the extracted material is then deposited on the growth substrate, forming a uniform film that has the desired composition, structure, roughness and thickness. The deposition process is carried out either in a vacuum or at a low gas pressure environment, which is achieved with the help of vacuum pumps and vacuum gauges that are connected to the deposition chamber. For instance, the amount of deposited material per surface area unit obviously depends on the distance between the target and the substrate. If the distance is greater, then less material is deposited. However, the film might also have a higher quality, as the energetic properties of evaporated material reaching the growth substrate often show optimum or sweet spot where the growth of high quality film is encouraged. The intensity, wavelength and length of the laser pulses also have a significant effect on the excitation mechanism that takes place on the target surface. For instance, using a laser with short pulses, shorter than 1 picosecond, electrostatic ablation occurs, in which case the electrons that hold the material together are excited so fast that they leave the material, resulting in an explosion of the small amount of target surface. When nanosecond or longer laser pulses are used, then the electronic excitations have time to relax, and the energy is transferred to lattice vibrations of the target. This is causing a fast heating of the surface and evaporation of the target material, which is called the thermal ablation mechanism. If longer pulses are used, then most of the impinging laser pulse is absorbed by the plasma plume, which further energizes the freshly created plasma. In either case, The interaction of laser pulse and the target material results in highly energetic plasma plume, which is directed away from the target surface. It should also be noted that only a small amount of matter from the very top layer of the target is excited and extracted during each pulse. This means that the deposition process is rather slow, but on the other hand, it also allows obtaining films that have a very high quality. In addition, this enables fine control over the thickness of the growing film. The pulsed laser deposition process can be carried out in various gas environments at different pressures. This is important because the pressure of the gas has a significant effect on the film growth rate, crystallinity and stoichiometry. For instance, the deposition of metal oxides is normally carried out in the presence of oxygen to ensure that enough oxygen is bound to the metal. The deposition of nitrides, on the other hand, should be carried out in the presence of nitrogen. It should also be noted that the kinetic energy of the particles arriving on the growth substrate depends on the pressure of the gas in the chamber. Using background gas reduces the kinetic energy of the particles and allows obtaining films with high crystallinity. At lower pressures, the extracted particles are not slowed down and they hit the substrate with a higher energy. This may cause localized damage and sputtering of the previously deposited film. However, when the gas pressure is too high, then the energy of the atoms arriving on the growth substrate is not high enough to allow the formation of an ordered crystal structure. The resulting film may be with low density and amorphous, which in some cases may be the actual goal. Anyhow, the crystallinity of the grown films also depends strongly on the temperature of the substrate. Films deposited at higher temperatures are normally crystalline, while films made at lower temperatures rather amorphous.
The tungsten boat is clamped between two electrodes. An electric current as high as several hundred amps passes through that tungsten boat, which undergoes resistive heating. Just like an incandescent light bulb filament, it heats up and glows. As the boat heats up, the metal source material in the boat melts and then evaporates. These evaporated metal atoms travel through the vacuum chamber, strike the surface of the substrate, and condense, forming our thin layer of the source material on our substrate.